Alright, now we have learned a little bit about torque, and remember that equation from year 10, F equals ma. Or, what we were basically saying was that force equals mass times acceleration, acceleration equals force over mass. Now we've got a similar equation in the whole rotational scheme of things. We've learned about our torque. We've learned the fact that it produces an acceleration. So do you think there's a similar thing? Something that we can put in there? Torque equals something times angular acceleration. Well, there is. And it's called rotational inertia, and its symbol is I. So it makes these equations real easy to remember. So I is like your equivalent to your mass. Mass was an inertia. Remember Newton's second law that said that your acceleration was proportional to the force and the mass? Well, similar situation, except rotation is quite special, okay? Because when we make something accelerate, we put a torque on it, it's going to get that clockwise acceleration, right? Angular acceleration. Sometimes I'm a bit quick to speak about things. What we're doing is we're accelerating stuff all at the same speed, right? But these guys, when he accelerates with an alpha, these guys are also accelerating with an alpha. But remember, the linear acceleration, A, is equal to alpha times the radius. So all these guys have different linear accelerations. So you can imagine the torque and the amount of overall angular acceleration is very much going to be dependent on the radii here, not just the mass, but the radii. So you actually end up with I equaling mr squared. That means that the amount of rotational inertia something has is not just dependent on mass, it's dependent on its radius, and its radius squared. So the inertia really builds up. It's like the mass increases because you're further away from the center of rotation. So if you double the distance, you get 4 times the rotational inertia. Now this is for a point at a certain radius. So if you had a disk, you've got to take your mass at a constant radius, which is impossible really. So every bit of mass at a distance from a center of rotation, this is the rotational inertia. So to actually calculate the total rotational inertia for this disk, we have to add up all the little masses and multiply them by their little radiuses squared. The little radius mean the distance to them. It might be this little bit of mass has a much smaller radius. That little bit of mass, slightly different one. We add them all up. And we can do that with things like disks because we know calculus. We're clever. And if we add all these guys up, then we come up with these formulas for different shaped objects. And the formula for a disk, for I for a disk, is actually equal to m, big M, that's the mass of the whole disk, rather than little m, little bit of the disk, times big R squared, but it's all divided by 2. Now, that doesn't surprise us. If all the mass of this big disk, all the mass was located at the outer radius, big R, then I for the disk would just be m big R squared. But some of it's got a very little rotational inertia, some of it's got the big mr squared, the big R squared, some's in the middle. So when you add them all up with calculus, and for the pain of it, I might do this in class, we will find out that the formula for a disk is that. Now, you can do other objects. We could do a sphere, a 3-dimensional object. We're going to need 3-dimensional calculus. We can do that. And we find that I for the sphere is big M, big R squared, but it's multiplied by 2/5. This was half. This is 0.4. So, and that's been done very exactly with calculus. What about a cylinder? Okay, you could have a cylinder, a hollow cylinder, right? if we had a hollow cylinder, what would I be? Well, a hollow cylinder, whoops, ran out of paper. A hollow cylinder, one like that that's sort of got a certain amount of distance, if all the mass is at this radius, right, then all the mass is at that radius, and if we rotate it about that center point, then it's going to be mr squared. So whenever you put a little bit of mass on something, for example, if we had a disk, if there's a bit of mass rotating, or we put a bit of mass on there, then if we know its radius, then we can say it's just mr squared. The disk itself, okay, has a specific formula, which was half mr squared. So this is rotational inertia.